Finally. You know how long I waited there for a personal interview?
Sorry.
That's all right. So, how many years do you think I'm going to lose from my lifespan by just being here? I see that there's quite a few freebies here. I asked how many years do you think I'm going to lose from my lifespan by just being here?
Oh, decades.
Right. Might as well make the most out of it.
Exactly. Enjoy the day while it lasts.
Where do I start? There's so much to see.
Good question. There's not really a theme going through this. It's just stuff.
A bunch of things we just threw together.
Yeah,
Okay,
exactly.
let's start from the right side.
Okay.
Okay.
These are photographic papers which I expose to radiation.
Right.
So this one was a small cobalt 60 source, and it took just about a day to get that spot.
Right.
This one is a fairly strong beta source, which also was just around a day. The other two, sadly here I had a light leak, but you could just about make out the uranium tile I had on there.
Yep. Is this the one stolen from that URS station?
I didn't steal it, but it's the same kind.
Right.
As well as this one. This was a bigger tile which had just a round rim of uranium.
I see.
Then I've got a few sources of radiation. These are uranium glass beads. This is a projector lens with thorium in it to raise the optical index. This is quackery, basically. These are stickers you can put on your phone to protect you from the dangerous 5G radiation. Only that it replaces 5G with alpha, beta, gamma.
Okay.
There's a lot of quackery on eBay. They all contain thorium dust, which is amazing because it contaminates everything. And this is an old compass with radium paint on it. It doesn't glow in the dark anymore, but you can still just about see it fluoresce.
Yeah.
Which is just, it's a nice source, I think.
Interesting.
Then we have a few more bits of uranium glass, which also fluoresce beautifully under UV.
And of course you have a bear.
Of course, I had to.
Nice.
And on the topic of fluorescence, we can go on to scintillators. Most of these are organic scintillators, which are very good for alpha and beta detection, not as great for gamma detection, and even worse for gamma spectroscopy.
Right.
But they glow beautifully and all kinds of colors, although this one isn't all that colorful. This is a plastic scintillator I made myself.
Okay, that looks really nice.
It's yellowed, I don't know.
Well, it looks professionally made as far as I can see.
That's the most important part. That's epoxy resin as a matrix, doped with 1 or 2% of this chemical.
Whatever that is.
It's the short name is PPO. It smells like utter shit. Yeah, but it fluoresces strongly, and that's basically what I'm using in there. I don't know, it's great for general purpose counting. It was just a fun experiment to make my own plastic scintillators.
Right.
Here we have a few inorganic scintillators. These are used in, for example, scanning electron microscopes as the electron detectors.
Right.
For reading out the scintillators, we've got photomultiplier tubes, which are just insanely sensitive light detectors.
Yeah.
So the scintillator itself, when it gets hit by radiation, emits visible light in the order of 1,000 to like 100,000 photons. And these things just count photons. So you get current impulse out of it, which is directly proportional to the number of photons coming in.
Right.
And that's pretty much all you do for the signal detection. So you got your particle coming in, the scintillator glows, this turns it into a current signal, and you measure that.
I see.
And depending on the scintillator, the pulse height of the current can be proportional to the energy of the particle coming in. And that's what I'm doing right here. So we've got the scintillator and then the photomultiplier tube. The rest is just readout electronics. And here, this graph is sorting the pulse height. It's pulse height spectrum, it's called. So on the x-axis, you've got the height of the pulse, of the current pulse you get, which is here it's lower, here it's higher. And on the y-axis, you've got the count. So every time you get a current pulse of some height, it adds just one to this graph. And when I take, for example, this cobalt 60 source, let me reset it. Fuck's sake, okay, worse. You can see, that's a bit too much. You can see these two humps growing, which are two different gamma energies which are emitted by cobalt 60. And once you've calibrated it, once you know which pulse height equates to which gamma energy, you can identify whatever you're looking at.
I see.
And cobalt is fairly simple to identify. It's got those two characteristic peaks. Another very nice spectrum comes from radium. But it's got a lot more peaks because it's got a long decay chain. It starts out as just radium and then goes through the whole periodic table down to that, basically.
Right.
And you can see these here are X-rays, which are emitted as a result of the decay. Its first peak is the radium itself, and everything after that is just decay products.
Right.
And by the ratio of those peak heights, you can determine the age of your sample and stuff like that. This isn't the best setup here because I've got sources everywhere and there's noise around. Usually you'd have this detector within like 5 or 10 centimeters of lead, and then you take some low activity sample, put it on there, wait a day, maybe a week, and then you'll see a spectrum like this.
I see. So it basically it's not exactly averaging out, so it's just accumulating counts.
Exactly.
So all the noise averages out and your peaks get higher.
Exactly. It's just integrating over a longer time. A friend of mine said it's like fishing. So you just sit there and wait for the one event to happen, and at the end of the day you'll have a bucket full, or you'll have a visible spectrum.
Nice.
So these are the scintillation detectors, and here we've got the gaseous detectors.
Right.
Most commonly of all, of course, the Geiger counter itself. Although most of these aren't actually Geiger counters, but proportional counters they're called. It's like a Geiger counter, built a bit different, and it retains a bit of information about the particle that hit it. So the system, for example, you can say if it should react to beta gammas or only to alpha radiation. We don't have any alpha sources here, so we can't really demonstrate the alphas. But you can see, for example, beta gamma, the background is fairly high at like 6 or 8 counts per second.
Ouch.
And with the alphas, it drops down to basically 0 because there aren't any alpha sources around. These are wonderful because they've got a huge detection surface area, and if you break the foil on there, it doesn't break the entire detector because these use lighter gas as a counting gas. You can just refill them and they work again.
Wow.
You can see here I had a small pinhole leak and I patched it with a piece of tape.
Yeah.
These are really, well, they're easy to break, but they're also very easy to repair.
I I see.
This is one of those detectors without the foil. And if you look closely, inside of all these channels there's a thin tungsten wire.
Yeah, I see it.
And that's the anode. And whenever a particle goes through there, it ionizes the gas. The anode is at a high voltage and just attracts the electrons.
Right.
And as the electrons get closer, they are accelerated and they bump into more gas molecules and ionize more gas molecules, produce more electrons, and it's an avalanche effect. And that's how you get decent amplification inside the gas of your signal and a very easy to count pulse in the detector. And if the amplification isn't too high, you still get retain information about how it started, how much ionization happened inside the gas. And that's how you can differentiate alphas and betas. Because alphas have a lot of energy and ionize a lot of gas in a short distance, whereas betas and gammas have less energy and basically fly through this all. And so you only get a few ionizations. This, for example, is your common household Geiger counter tube. It's beautifully made. It works on the same principle, but in Geiger counters the gas amplification is high enough that the amplifier basically saturates.
Right.
So you don't retain any information, but you get the highest possible signal, which is why Geiger counters can be built fairly simple. These two are proportional counters, just like this one, but they're filled, or this one used to be filled, this one still is, with helium-3 gas, which undergoes a nuclear reaction when hit by neutrons, and so these can be used as neutron detectors.
Right.
This is just another Geiger-Müller tube, same as this one. This is a Geiger-Müller tube as well, but it's got a huge window there, just to make it more sensitive to particles that are more easily stopped. So this one, for example, would also see alphas.
Right.
And this is a wonderful rate meter, which just supplies high voltage to the detector and then counts the pulses coming off. So if I take, for example, uranium here, you can watch the needle go up and hear it tick. You could hear it tick if it wasn't so damn loud here. And these straws, fairly nice. They're part of the Atlas detector at CERN. They form the transition radiation tracker. They're basically just proportional counters as well. So these are built like that, only in weird proportions. This is just a cathode. This would be an anode wire for it. So you can see this is 12 micrometer tungsten wire.
Wow.
Which you would string all down that tube.
Right.
Fill the tube with xenon and CO2. And then have it work as a proportional counter. Take 500,000 of these and you can track a particle going through the detector. You want it?
Of course I do. Thank you very much.
And speaking of freebies, we even got some uranium.
That's amazing.
These are small beads of uranium glass. They fluoresce nicely.
Nice.
And each contain a few milligrams of uranium. Just enough to detect them with a decent Geiger counter. And you can use them as check source if you want.
Nice. Do you mind if I pick one of these up when I'm leaving? I have nowhere to put
no,
it.
not at all.
Yeah, perfect. Thank you. But these I can probably put them in my pocket. So I'll probably die a couple of years early, but I think it's worth it just having a few milligrams of uranium. Thank you very much.
Sure, no worries. And this is a project made by a friend of mine. It's an Internet of Things Geiger counter and humidity sensor and all of that.
I wonder if it can...
No.
Not really.
The plastic around this is enough to shield basically everything coming from those.
Okay. Right. Interesting. Wait, is this the detector or
No,
is...
this is the Geiger tube.
Uh-huh.
This is for humidity and
Oh, right.
temperature and pressure as well.
Interesting.
It's a fairly nice little detector, and if I remember correctly, his goal is to make an open source map where lots of people have detectors like this, and you can just map out whatever happens in the world, basically. So there were a few nuclear accidents which got detected delayed because the networks that are currently set up for radiation detection are very bureaucratic, let's say.
Okay.
And an open source detector like this would make it a lot more efficient to detect everything quicker.
Interesting.
But I'm not too versed in the exact details here. There's a QR code to his website.
Yeah.
And he'll give a talk today at 4 in the afternoon, I think, where he explains it all.
Right. Looking forward. So, I think we basically covered everything here, but now I'm curious to know what this is.
Sorry?
I'm curious to know what this is.
The Organspendeausweis is something you put in your wallet. So if you get in an accident and you die, they know if they can harvest your organs.
Right.
Harvest might sound a bit harsh. It's all, basically a donation organs.
That makes sense.
These are free. Take them. Take as many as you
All right.
want.
I guess I'll take one of each. I don't. I kind of have mixed feelings, but sure, I'll take one.
No. You can also say, don't take anything.
Okay, so an organ.
These are just so it's
Donation.
clear what you want.
Ah, okay.
You don't glass.
Right.
And they can tell you a lot more about it than I can.
Of course.
So these are all self-made glasses, molten from oxide powders in a little furnace at about 1,200 degrees.
Right.
And the different metals give the different colors. So this is copper oxide, chromium, cobalt, manganese, europium, and some of them
This
fluoresce.
looks really nice.
And the europium fluoresces under 395 nanometers, and the terbium under 365.
Right. So it basically looks transparent, but when you shine a UV light
Yes.
on it, it glows. It's really
And
interesting.
this is magnetic glass.
Wow. And what exactly makes it magnetic?
The gadolinium ions,
Right.
rare earth element, and it's fairly high concentration. It's about 40% gadolinium in them.
Nice. Oh, and I assume I can,
Yeah, but you have to populate it yourself.
of course.
But, and then you get this Geiger counter.
Right. Are these free?
If I've only got 4, so if you are planning on populating, you can take one.
I am not so sure if I will be able to find all of the parts. So I
The
guess I'll
parts
just...
are the more exotic parts.
Uh-huh.
Got ordering numbers from DigiKey or LCSC, and the rest are standard resistors and capacitors. You find them everywhere.
Right. Maybe next time.
Okay.
I'm not so sure. All right. Oh, and what about this?
This is a polariscope. The light has a polarizing filter on it, and another polarizing filter 90 degrees, and you can see the stresses in plastics. So the colors change when you rotate it.
Right.
And this is a little handheld version. You hold up against the light and have the same.
You put your
effect.
sample in the
Yes,
middle and...
yeah.
Right. I see. All right.